derivatives and antiderivatives, I guess. So we can go forward and backwards with these things, and it's true for the regular functions we've dealt with in Calc 1 or 2, and it's true for vector functions like these ones. So I suppose we should just get to it. Let's try to find an application that might have something like this. And there's one that I guess when I was a student I had. It's about shooting an arrow and stuff. So let's take a look at a couple of two-dimensional examples, and then we'll try to bring our ideas to 3D. So let's take an example where we shoot an arrow. Let's see, an arrow. Here's our arrow, and that'll be our projectile, and then it gets shot, and eventually gravity is going to pull it down, and it'll land on the ground. So if we give ourselves some measurements here, like maybe define how high this is when it first takes off, and then define an initial velocity of getting shot off, we can get information, and also assume that there's some sort of acceleration. Then we should be able to find out some information about where this lands, how fast it's going when it's landing, etc. So let's do that. Let's say, should we do meters or feet? Meters. Okay, so if you're standing up, shooting an arrow, how high is that off the ground about? 3 meters? Do you really want to do meters? This is a meter. Oops. What are we looking at? 1.5? Let's do meters. Okay. Now, you pull this arrow back and then you let it go. We're going to need some information about the initial velocity, like how fast this is going to go. So for that, let's just make something up, and then maybe we'll adjust it later. So let's make up something. How fast is something going? Meters per second. What? 15 meters per second. So we shoot off with an initial velocity . Well, I'm not going to put an arrow on top there yet, because the whole idea of this right now, initial velocity, is that this is a speed, 15 meters per second. Because this is a scalar. When you say 15, that just seems like it's a scalar to me. So we'll keep it V naught as a V naught without an arrow, and then we'll talk about when V naught becomes an arrow or becomes a vector. And let's do an initial gravity of what's the gravity? 9.8. Now this is we'll assume that up is positive and down is negative, so gravity is pulling down. So let's throw a negative sign here. And since we are talking about this in 2 dimensions, the down gravity gives it the up and down direction, so that's the j direction. And so we can put this in a 0, negative 9.8 vector, or we can just write negative 9.8 meters per second squared in a j direction. And that should be enough to provide our acceleration. Okay? So the kinds of questions we can ask are, where does it land, and what's the speed? So we can ask a couple of questions. Where does the arrow land, and what's the speed? At impact. Okay. All right. So one of the things that we probably need to do is that we're actually doing differential equations here. We're starting off with a second derivative of something, and we're trying to obtain the position to figure out where this is going to land. And so we are dealing with vectors, and so it would be nice to change everything into vector form, points or vectors, however you want to look at it. So if we take a look at the velocity, the speed right now is 15 meters per second we're looking at. I guess we should also establish, and I'll do that now, we should also establish maybe an axis where the x-axis is and the y-axis is. So maybe if we call this starting point of where the arrow takes off the y-axis, and then the ground to be the x-axis. We can better assess the positions of things. And so now let's go back to the idea of this velocity. This velocity right now is not a velocity, it's the speed. If I want to make this into a true velocity vector, we need components of this. Now, you're shooting the arrow horizontally. So what can you say about one of the components of this? Which one? The y component is going to be equal to 0, right? And so this is going to go in a positive direction, 15 meters per second direction. And so we can say that the velocity vector itself, let's call it the initial velocity, so the sub-zero there is important. And then we'll say it's going 15 meters per second in the j direction, in the I direction, sorry. And then in the y direction, or the j direction, it's going to be 0 because we're shooting it horizontally. So in differential equations, when you have a second derivative of something that you're looking for the original function, and it's an initial value problem, you need two initial values. So from the acceleration, you would need the initial velocity, and then you would also need the initial position. And so that's the other thing that we're going to need to find. We need to find out where the initial position is. And we'll call that r sub 0. And we can refer to it as a vector in standard position pointing to the point, but it's really a point. So where are we? What's our starting point? 0, comma what? 1.5. That was our height of that arrow as it took off. Okay? So, I don't know, it's better to use i's and j's, or if we use the bracket formation. The i's and j's, you're kind of not seeing the 0i, but it's there, because when you take the antiderivative of 0 in an indefinite integral, you're going to come up with a constant. Okay? So I'll leave it as i's and j's, and then we'll integrate this. And then do we want a constant sitting on the outside, or do we want a constant in each of the components? How did we do this last time? Outside, so let's have a constant on the outside. So we integrate this once, and we get our velocity vector. In fact, let's maybe label it as the antiderivative of the acceleration. And then there's no I component. We'll have a constants on the outside. And then there's a j component. You integrate 9.8, negative 9.8. You're going to get negative 9.8t. And then I'll save the units on the outside. This is in the j direction. Plus, now here's your constant. You have some constant in the I plus another constant in the j direction that we need to consider and be able to solve for. And the way we're going to solve for this is with the initial conditions. In our case, we're given the initial conditions for the velocity. We know that when t is equal to 0, assuming that the initial conditions happen when the time is equal to 0, we know that it's supposed to be 15 comma 0. So let's put 0 in for t here. V of 0 is equal to negative 9.8 times 0 is 0. So we just have c1 in the I direction plus c2 in the j direction. And that's equal to, it's supposed to be equal to v naught, which is 15 and 0 in the j direction. So you have your C1 and C2 essentially solved for here, right? So it looks like C1 is going to be equal to 15. Those are the I components set equal to each other, and the j components set equal to each other. C2 must equal to 0. So then you can finalize your velocity vector to look like, let's do the I first. That's 15, a constant in the I direction, plus negative 9.8 t plus 0 in the j direction. And that's meters per second. So now we have information about the velocity. Okay, so far? Yes? Over here? When we integrate, we're really integrating the integral of 0 comma negative 9.8 dt. And so when we integrate this, we integrate 0 and we get a constant out of that. And then negative 9.8 t plus another constant. And so that's C1 and C2 are here. Well, it has to go in all directions. When you integrate in the x, there's going to be a constant in the x. When you integrate in the y, there's a constant in the y. So there's constant in all the components. And so you can do it component-wise like this, or you can do it with i's and j's like this. Okay? So when we did this, I guess one time when we're talking about integrating, we call this C with an arrow on top. And I just wanted to separate it because we were on our way to solving stuff. Okay? All right. Now that we have this, we can go ahead and integrate again because we know that the integral of the velocity should give us the position, and that's really what we want. Once we have the position of a projectile, we know everything about that projectile. We know its height, we know how fast it's going, all kinds of stuff. We know its positions. So we'll integrate again. Maybe I'll try doing the integral with the constants within the components. Let's try that. So if I integrate 15, I'm going to get 15t plus a constant. And I use C1 and C2. Let me use another letter, D1. And then the antiderivative of negative 9.8t should be, what is it, 4.9? And there's no constant, but there's a 0 there. I mean, we integrate that, we're going to come up with another constant, d2, in a j direction. And we know that when t is equal to 0, r of t, r of 0, is equal to d1 comma d2. I'm switching notations again. And this is equal to 0 comma 1.5. Remember our initial position? So d1 must be equal to 0 and d2 must equal to 1.5. So our position function should equal to 15t plus 0 and then we have a negative 4.9 t squared plus 1.5. meters, because we took the integral antiderivative with respect to time. So, okay. So now we can answer the question, when is this going to hit the ground? And then how fast is it going at impact? Out of space, so I need to take this to the next page. So, to answer the question, where does it hit the ground? What function should we use? And what should we do? Yeah? We should set the origin at the ground. So we should look at the position function and set the y component of the position function equal to 0, because that's the height. So we're going to set negative 4.9 t squared plus 1.5 equal to 0. This is our height. And then that's going to give us a time when this is going to happen. So it looks like t is going to be the square root of 1.5 divided by 4.9, which is approximately, anyone? 0.55 seconds. Can we get a confirmation on that? Anybody else punching in their calculators to see? 0.553. Okay, so we have the time when this thing is going to hit the ground. What do we do with that? What? Plug it into the I component. So R of 0.553, if you plug it into the whole function, you know your J component is going to equal to 0 because you just solved for that. So you take your 15 times t, and then that's going to give you, essentially give you the distance. So Half of 15, that's like 7-ish. 8.3 meters. That didn't go very far. Boing. This is your first arrow that you shot. So 8 of these guys. I can throw it farther than that. All right. Yeah, I know. So 15 meters per second seems a little slow. Yes?
Why are we using just the negative 12.9 squared?
Because this gives us the height. So this gives us our position. At any time t, we can figure out the height by looking at the j component, and we can figure out the distance by looking at the I component. So when the height is equal to 0, in this case, we're on the ground, and by taking this time, and then you put it into the I component, you're going to find this distance, 8.3. Okay? Now, how fast was it going? To answer the next question. What is the speed at impact? How do we determine speed? The t that we found is when it hits the ground, so that's the impact, yeah. What are we going to do with that? Well, we put it in the velocity equation. Now, if we put it in the velocity equation, let's see what happens when we put it in the velocity equation. So v evaluated at that 5.553 number is like putting 0.553 in here. So we got 15, comma, negative 9.8 times 0.553. So I get 15, comma, whatever this is, some negative number it looks like. I'm going to guess about 5 point something, 5.4. Does this give us speed? It gives us a velocity. It tells us when we hit this thing, we're going in a positive x direction and a negative y direction, which makes sense. Speed is the magnitude of the velocity, right? So speed equals magnitude of the velocity. So just find the magnitude of that. 15. How do you find magnitude? You square it or something? 5.4 squared. And so whatever this is. Say it again?
I got 15.9.
So you shot it off at 15 meters per second, and then it picked up a little speed, I guess, as it started to go down, and then it went almost 16 meters per second as it landed. So that's how fast it's going. Okay. So that's motion in space. Or no, we're not in space yet. That's 2D motion. Any questions? All right. So we can use the same scenario, make it a little bit more interesting. and do some physics. This is like really physics, right? You guys have seen this in physics classes. I really don't like physics. All right, should we try to hit a target? Or should we just hit a big wall? Let's hit a target. Ooh. So this time, this time you're going to shoot your arrow at an angle. And then you have a target. And you're trying to hit. So we'll use the same 1.5 meter height. And then let's put the target at 30 meters away with a height maybe 1 meter up. And let's say you're going to shoot this arrow at a 45-degree angle from the horizontal. And let's say you're so good that you have total control of the velocity of the speed of which your arrow is going to fly off. And at this point, we don't know what that is. We'll call it the velocity. And we'll not put an arrow on top of that to say that this is a scalar. And so now the question is, what should your velocity be so that your arrow will hit your target? Okay? Is the question clear? Correct. Yeah, so we need vectors, right? Well, again, we'll start with our acceleration being negative 9.8. And now we need to come up with initial position, initial velocity. So those are the two pieces of initial conditions that we need to be able to solve for this differential equations. And I think the position is still the same. And that the r of 0 is equal to 0, 1.5. But now velocity vector, last time we shot on the horizontal, so we kind of reasoned this idea that it's just going to, there's no I or J, there's no J component to it, so that's 0, and then everything, all the speed went in the horizontal direction. But this time, your speed goes up, you're at an angle, and not only that, your speed is also unknown, so that's trickier. And so what we want to do is, what I want to do is try to figure out what this vector is. do some trig, right? For those people who have taken physics before, you know that there's a sine and cosine involved in this. And if you haven't taken physics before, there's a sine and cosine involved in this. So if you look at the arrow, you want to find the x and the y components of that arrow. And the x and y components are just the opposite and adjacent sides to that right triangle. And so you can create your trig with opposite over hypotenuse, and the hypotenuse is some unknown that we're going to solve for, but it's a constant v naught. And then the adjacent is going to be the cosine of whatever. So the x component here will give us our cosine function because that's the adjacent side. So it's going to be not an arrow, just the speed, v naught, which right now is unknown, times the cosine of the angle, which we set to be 45 degrees. And then we have the sine of 45 is going to equal to the opposite over the hypotenuse, which is v naught. So this would be sine 45 degrees. And we know what the sine and cosine of 45 degrees are, right? It's like root 2 over 2. So really, we can just say this is equal to root 2 over 2 v naught if we factored it out or multiply it in or whatever. But we're going to eventually need to solve for v naught somehow, somewhere. So any way you look at it, you can set it up like that. All right, let's integrate the acceleration function. And we'll get v of t. So the integral of 0 is a constant, c1, and negative 9.8 t plus c2 is the integral of the second part. And then we're going to let t equal to 0 again to get our initial value. So when t is equal to 0, we're going to get c1 comma c2. And that's equal to the initial position. That's root 2 over 2 v naught comma root 2 over 2 v naught. So c1 and c2 must equal to root 2 over 2 v naught. So I usually like to just rewrite it over again so it'll get me ready to integrate to find my position. So I have root 2 over 2 v naught comma and then negative 9.8 t plus root 2 over 2 v naught. And for those keeping track of units, we're in the velocity stage, so this is meters per second. And if you're, I don't know if they do this in physics, but they skip a bunch of steps in physics and just, you know, when you set t equal to 0 business. So it turns out that if you have nice polynomials like this, it turns out that your constants will always be your initial positions, initial velocities, and stuff like that. However, if your functions are not polynomials, like they involve sines and cosines or exponential functions or anything else, it may not work out that the constants are the same as the initial conditions. So you just want to be careful about that little piece of information. All right, let's take it to the position by integrating the velocity. Root 2 over 2 v naught plus a constant from the I for the I direction The integral of this is 4.9 negative t squared plus root 2 over 2 v naught t plus something else. And with this business about letting t equal to 0 again, we're going to get d1 and d2. Because these are polynomials, they're just going to be equal to the initial positions that we had. So 0 and 1.5. So that will give us our real position. That's root 2 over 2 v naught plus 0, comma, negative 4.9 t squared plus root 2 over 2 v naught t plus 1.5. And we're doing this in meters, so that would be our units. Yeah.
When integrating from the velocity vector to the position vector in the x direction, how come there's no t on the root 2 over 2 v naught? Where you go adding the d, yeah.
Oh, because we got this to be 0.
Okay.
Anything else? Are we doing this correctly so far? Pardon me? Oh, he was asking why this disappeared, and it turns out that d1 was equal to 0.
How come there's no t on the v naught?
Oh, because you couldn't see it really well. It's right here. Thanks. All right, so our task is to make it hit that target, and that target, our arrow is eventually going to hit the target at some time, which we don't know, and at some velocity. And it turns out that if you want to hit the target, the target will be at 30, 1. So eventually you want your position to be there. And so it looks like we can just set these two things equal to each other, the component by component. And then we'll have two equations and two unknowns. So let's pick it up from there. And set them equal to each other. And I don't know what the best way to solve for this is, but we can decide. The nice thing is that the first equation looks like it's easy to solve for. We can solve for either t or v naught, and then put it on to the other equation. The t's looks like they're going to be squared in the second equation, so I don't think we can get away from quadratic formula later on. And I don't know if it's going to matter which one we do. So pick one. Solve for v or t. Yeah.
But if you solve for v naught, the top one, you sum it in the t.
Oh, nice. Okay, let's do that. So let's solve for v naught here. V naught is equal to, let's put this 30, 60 over root 2. And then the t goes in the bottom also. So we'll put that into here, and then we're going to get negative 4.9 t squared plus root 2 over 2, and then the v naught is a 60 over root 2 t in the denominator. That would cancel with that t in the numerator. Thanks, Harrison. And 1.5 is equal to 1. Suppose we can clear that out already. Let's cancel the t's out here. What? We could? Oh, yeah, okay, there you go. Well, we're here already, so. Any way you can, solve for this. So that whole thing becomes 30, and that's that 30 that, yeah, you were talking about. We'll bring that over to the other side, and then we'll bring the 30 over to the other side. And then so eventually we get negative 4.9 t squared is equal to, what is it, 30.5? Is that right? 30.5? Negative, but that negative is going to cancel with this negative, which is good because we want to be able to solve for this. I guess we could take the square root there as well, and of course we would just consider the positive square root. So, what do we get? Can we get a confirmation on that? Yep. All right. So in 2.49 seconds, this arrow flying is eventually going to hit our target. But that's not what we want, right? We want the velocity. And we have the velocity already solved for here. V naught is equal to 60 over square root of 2 times that thing that we just found, 2.49. And what's the velocity there? Confirm. Yeah. So this is a velocity, meters per second. This is a speed that we need to shoot the arrow off. It's not much farther than 15 meters per second that we had in our first problem. So if we shoot this off at about 17 meters per second, we should hit that target. Okay? Any questions? Okay, that was fun. So, we can bring this up to 3 dimensions if we want. I mean, not if we want. We will bring this up to 3 dimensions. And it's going to be the same idea. We're talking about the acceleration to the velocity to the position, and once you get the position, then you figure out, just logically try to figure out, answer questions like what's the highest point, whatever. So let's do one of those problems. I was going to try to come up with one, but instead I'll just have to use one of the old ones. I know the Giants are practically out, but let's do a baseball one. So, you're playing baseball, you see a fastball 3 feet above home plate, you swung and hit the ball with a velocity of 80 in the I, 75 in the J, and 60 in the K direction. Assuming gravity and some slicing force, the acceleration is given by 2 in the I when the ball spins, it curves left, right. So let's say it curves in the I direction, and the gravity is 32 feet per second in the J direction. In the K direction, we're in 3 dimensions. So, find the velocity vector, that's the function. Find the path of the ball, that's the position. And what is the maximum height? And if the fence is a circular arc around home plate, 380 feet away, and it's 12 feet high, did you hit a home run? Okay? So this was an exam problem a few years ago. There's a lot of stuff up there. Where do you start? Draw a picture. Drawing a picture is always a good start. So I'm going to draw the picture from the point of view of maybe behind home plate, maybe a little bit off to the side from home plate. So this is your home plate. Then you have first base, third base, second base. That's the infield, and the outfield's a long way away. You got a little circular fence out there. There's a mound. Okay, now we got the picture drawn. What do we do? Do we want a guy there too? Yeah, since we have acceleration, that's a good place to start, right? So let's get our acceleration written down here. And I'm going to change to the bracket notation so I could see the components that are not there. And more specifically, there's a 0 and a J, so I want to make sure that I acknowledge that there's a J component here. So when your acceleration is constant, that makes it kind of nice for us to be able to use the initial conditions. Oh, speaking of initial conditions, we have them, right? We have one of them clearly written up here. What's our initial condition for the position? Zero. So what is it? 0, 0, 3. This is 3-dimensional, so the height is in the K component, the third component. So we can say that this is home plate, 0, 0, 0. This is the x-axis maybe, using the right-hand rule. This is the y-axis. And then the z-axis goes straight up. So the z will give our height. We are some distance away from the fence, the outfield fence, 300 and something, 380 feet and 12 feet tall. We'll deal with that when we get there. Okay, we got our acceleration. Integrate the acceleration. Integral of the acceleration vector is the velocity vector, and the velocity vector is going to be 2t plus a constant. And then there's 0 there, so we have to acknowledge the constant that would come up in an antiderivative, because the derivative of the constant is 0. And then we have negative 32t plus a third constant. So we have the constants that we need to figure out, but if you put 0 in for t, you're just going to have c1, c2, c3, so that's exactly going to be whatever the initial velocity is, right? So when t is equal to 0, you got v of 0 equals c1, c2, c3, and this is supposed to be equal to v naught, which is 80, 75, and 60. So just to rewrite everything over, we got our velocity vector to be 2t plus 80, comma 75, comma negative 32t plus 60 meters per second. Okay, I'm just integrating along. Yeah. Feet. Thank you. Feet per second. Doesn't look like. Okay. Let's integrate again to get our position. So 2t squared is over 2. It's just going to be t squared. We got 80t plus a constant. Antiderivative of 75 is 75t. And then you throw another constant. And then antiderivative of negative 32t is negative 16t squared. Antiderivative of a constant 60 is 60t, and then we throw in a third constant. Again, when t is equal to 0, all you have are the constants. The constants then should be equal to the initial position, which is 0, 0, 3. So we got our position to be t squared plus 80t plus 0, comma 75t plus 0, comma, negative 16t squared plus 60t plus 3 feet. So part A is looking for the velocity. Part B is looking for the position. What's C asking for? Maximum height of the ball. Yes. So a projectile, it's dependent on the velocity, right? And the velocity is 0 at the maximum height. So look at your graphs of your parabolas. They have that maximum height that you achieve. So that happens when the velocity is equal to 0. Or if you want, you can look for the vertex of this polynomial. We're not going to do that. So the max height, z, what did you say, Matt? Z component of the velocity equal to 0. Okay? So we'll take our z component of the velocity, negative 32t plus 60, set that equal to 0. T is equal to 60 over 32. I was going to try to reduce that, but got too hard. Oh, there we go. So that's the time. That's how many seconds it takes for the ball to reach the maximum height. But what is the maximum height? Plug that into the position, right? Whenever they're looking for a place, where is this happening, including maximum height or where it hits the ground or where it hits something, the position is going to be involved. When they're looking for, like height thing, that's velocity. So let's take this and put this into the position function, but we really don't need to put it into all the components because you just don't want the height. I mean, we can put it into the x and y. That will tell us exactly where on the xy plane it is, but we just want the height. So plug back into R, more specifically the z component, because that's going to give us the height. So plug that into the z component. We got negative 16 and then the 15/8 squared plus 60 times 15/8 plus 3, and then whatever this is should be our answer. So what is it? 59.5. Can we get a confirmation for that? We got another nod of the head, so let's say that's good, and that's the highest point of the ball. So it is 1:47. It is the weekend coming up. If you want to complete this and submit the whole thing from start to finish, all the different parts of this problem, if you give this to me on Monday at the beginning of the class, I'll give you, and it's correct, I'll give you 1 point extra credit on our next test. But before you go, I want to make sure that you can find the review sheet. Yeah, I'll put this up in the notes. So I've shuffled things around a little bit. I used to have other stuff down here. I used to have the agendas for week 1 in separate modules, but now I've changed to put all the agenda items in one module. This is a module, weekly agenda, and then other stuff in handouts. By the way, there's been postings here, note sharing, and are you writing this yourself, or?
Oh yeah,
Yeah, so GeoGebra, right? Is that what you're using?
I'm using Desmos, which is online. So
So there's a cool graphical program that Mariah's been working on, and she's been posting stuff. So if you're interested in taking a look at that, I highly encourage that because they were looking good. And there's some other responses over here by people. So the discussion board's there in the home page, but I wanted to point out that our information about exam 1 is here. So if you click on this, by Monday, and during class I'll share it with you, I'll eventually have an outline of how the exam will look like. Meanwhile, you can download the review sheet, and this is the exam that I gave in last year's class. So I don't know if our I don't know if our exam will model that exactly, but if you can get a feel for how I give exams for those people who have never had me before, nobody's ever had me before, for all you guys, you can get a feel for what kind of questions I ask. So between these questions on the review sheet and some of the questions that I just did today, those are the kinds of questions that I tend to lean forward toward. Okay? You will have a sheet of notes. You can write whatever you want on those notes, from formulas.
Or a like note card.
8.5 by 11 sheet. Back and front, you can write formulas, you can write examples, you can write a poem, you can draw a picture, you can do whatever you want on that sheet. No. You can do whatever you want on that sheet. So because of that, I'm probably not going to ask you simple questions. So the questions that I tend to ask, if you look at what's happening in these exams, the kinds of questions I ask tend to be a little bit more stretched out beyond the basics. And that's because you have a sheet of notes. Okay? William?
We're expected to have like critical formula.
I don't care what you put on the sheet of notes. So
If we didn't bring in a sheet of notes, would there be like a question that we should have had like a formula for that we would now know?
I don't know. I mean, I can, like, for example, if I ask you what the distance between a point and a plane is, I'm not going to give you the formula because that would be something that you should have in your sheet of notes. And if you don't bring in a sheet of notes, then you have to either rederive that formula, try to remember it, or you're screwed. Yeah. But that's, I'm going to expect that you're going to write whatever you want to write, and I'm going to ask questions that may or maybe or may not be on your sheet of notes. Okay? All right. Good luck studying.